Hello, in this video we are beginning our Unit 4 discussion, and this first lesson is called Related Rates. Now, Unit 4 can largely be summed up as optimization, how we find optimal results for a given problem. And we'll talk a little bit more about the phrase optimization later, but it's a big concept in calculus and it has lots of real-world application. So before we answer any questions about optimization, let's talk about this notion of related rates. In this first example, we've got an oil rig that springs a leak in calm seas, so there's no current that's pushing this along. The oil spreads in a circular patch around this rig. So let's just imagine for a second that an oil leak is sprung right here at the center of this oil rig, and as time passes, this oil patch is going to be getting larger and larger and larger. Hopefully you can kind of envision that as time passes, the radius of this oil leak is going to be getting bigger and bigger and bigger, and ultimately the area affected by this oil leak is getting larger and larger. Now, if the radius of this oil patch is increasing at a rate of 30 meters per hour, we would like to know how fast the area of the patch is increasing when the patch finally reaches 100 meters in radius. Now, the reason why that's important is, let's just assume for a second here that this patch is increasing at 30 meters per second. Well, as the patch gets larger, if it's a small patch and it's increasing by 30 meters per second, the amount of area associated with that increase is one size. But if our radius is larger, like 100 meters, and it's still increasing at 30 meters per second, the amount of area associated with that increase, once the circular patch is larger, well, that area is much larger too. It's quite a bit larger as well. And so that's what we're trying to focus on. Since the area is changing at a different rate as time passes, we would like to know how the area is changing at this particular moment. And believe it or not, this problem is very simple, or I should say it's very simplified compared to real-world examples. There are no currents to affect the shape of the oil patch. The rate is increasing at a constant speed. The oil patch is increasing at a constant rate, a constant speed. So a lot of things are going in our favor, but this allows us at least to talk a little bit about the process in general. So I'm going to start with this good old formula. Area is equal to pi r squared, because this is the area formula for a circle. And we were told that our oil patch is growing in a circular shape. Now, even though the radius is changing and the area is changing, and we can represent the rate of change in radius and the rate of change in area by using a derivative, what we're really focusing on is how the area and how the radius is changing with respect to time. And the problem doesn't explicitly state that time is an additional variable in this situation, but it is sort of implied over here. We had a unit of time in this measurement. So the radius of the oil patch is increasing at a rate of 30 meters per hour. That's a rate, and therefore it could be considered as a derivative. And in fact, it should be considered as a derivative, because the rate of change of the radius with respect to time, the change in radius with respect to time, is essentially a derivative. And we actually have a value for that component that we'll see its use in just a moment. We're going to be curious about this related rate precisely when the radius itself is equal to 100 meters. I better be careful here. Meters per hour. We'll include our units. And then back over here, when we talk about the actual question in the problem, how fast is the area of the patch changing? Well, fast, that's an indicator of speed. That's a rate. How fast does the area change? What's the rate of change of the area with respect to time? That's what we're looking for. And lastly, the area of that circular patch itself can be calculated by using this formula when R is equal to 100. We'll cross that bridge when we get there. So I'm going to eliminate these highlighted marks for just a second. And now we're going to apply that old technique that we discussed just last week, this notion of implicit differentiation. Because what we're doing is we're going to be deriving, or we're going to be finding the derivative, I should say, of both sides of the equation with respect to time. And the more you practice these problems, the more you'll recognize the variable at which we're deriving and how to handle these particular derivatives. But just like we said during our implicit differentiation unit, if we're deriving a variable based on another variable that disagrees, we don't really know what that derivative value is. So I don't know the derivative of a with respect to t, so I'm going to leave that as this notation. In fact, that's a good thing because that's what we're after in the long run. Now when we take the derivative with respect to t of this expression over here, we see a couple of interesting things. Much like the derivative packets that we assigned last unit, we're being asked to find the derivative with a unusual constant. It's not a numerical constant that we're used to seeing, but a Greek letter constant, but that's okay. But also we are taking the derivative with respect to t and not r, so we've got to account for that as well. Now the derivative of pi times r squared would be 2 pi r in terms of r, but again, since the r and the t variable disagree, we have to tack on this additional phrasing here as sort of a mini chain rule. And if we think about what we have, we'll just kind of remind ourselves here, this is the rate. It's a rate because it's a derivative, and it's the rate of the area changing, the rate at which the area changes. And r, this variable here, is simply the radius of the patch. And then here's another derivative, so we'll call it a rate. All derivatives are rates. This is the rate of the radius as it changes. And fortunately for us, we were given lots of this information. This rate at which the radius is changing is given to us, as well as the radius of the patch itself. What we didn't know was the rate at which the area was changing. That's what we're going after here. So that's no problem for us. We've got values for virtually every other component. So the rate at which the area is changing based on time is equal to 2 pi times our radius, which is 100 meters, and multiplied again by the rate of the radius as it's changing, and that's 30 meters per hour. We can multiply these components together. Now, I'm not going to worry about pi being some decimal value. I'm going to leave this answer in terms of pi. But 2 times 100 is 200. 200 times 30 is 6,000. So we have 6,000 pi units. And let's think about our units here. If I had a, this is just side notation here, if I had a meter unit, it's kind of like meter over 1, times another meter per hour unit, then what we would end up with is meters squared per hour as we multiply our units together straight across. And that's perfect for us because the answer that we were going for is the rate of change of area per unit of time. And meters squared represents our area, hour represents our time, and we have a wonderful answer that actually addresses the question here. When the oil slick is 100 meters in radius, the area of that oil slick is growing at a rate of 6,000 pi meters squared per hour. By way of comparison, if we had caught this oil leak not after 100 meters of growth, but instead of only 5 meters of growth, which, by the way, 5 meters of growth at 30 meters per hour would have been caught after 10 minutes, whereas 100 meters of growth would have taken 3 1/3 hours, or 200 minutes have passed. So, I don't know how operating on an oil rig works, but if there's a spill and we can contain it after 10 minutes as opposed to waiting 200 minutes to contain that spill, well, that oil spill after 10 minutes is only growing at 300 pi meters squared per hour as opposed to 6,000 pi meters squared per hour. A very, very big difference. Let me share with you another example. We have two airplanes that are converging on an airport, and one of them is flying due west at 120 miles per hour. So we've got this airplane that's flying due west, and it's flying at 120 miles an hour. Now, I'm going to call this, like we normally would, the x direction. This horizontal movement is x. And since the distance to the airport is decreasing, I'm going to say something like this, that the change in x position with respect to time is equal to negative 120 miles per hour. For most of our related rate and optimization problems, signs do matter. And while this negative number doesn't necessarily mean left or right in this case, I chose the negative identifier because the distance to the airport is decreasing. Now, the other airplane in this problem is flying due north at 150 miles per hour. So it's flying perfectly north at 150 miles per hour. So I'll call this dy dt, the change in y position with respect to time. And here again, since the distance to the airport is decreasing, I'll call this negative 150 miles per hour. I'm going to scoot this up a little bit because there's part of the diagram that this might interfere with. So dy dt is negative 150 miles per hour, and dx dt is negative 120 miles per hour. And I know that those are dy dt and dx dt because they are both rates. Look at the units associated with those numbers. The units are fractions, therefore we're talking about rates. To make this problem easier, we're assuming that they're flying at the same and constant elevation, so they're not rising or falling. That would affect our distance. We would like to know how fast is the distance between the planes changing when the westbound plane is 180 miles from the airport and the northbound plane is 225 miles from the airport. So the x distance is 180 miles. This airplane apparently is 180 miles from the airport. The y distance is 225 miles because this airplane is 225 miles from the airport. What we're interested in is the distance between the two. Now the distance, z, is easy to calculate. We have the Pythagorean equation that can help us there. Z squared, we know, is equal to x squared plus y squared, or z by itself is the square root of x squared plus y squared. I actually think this formula might be a little bit more helpful in this problem, and you'll see why in just a second. But the problem itself is asking how fast is the distance between the planes changing. So when we're talking about fast, how fast something's going, this is a rate. So when we're talking about a rate, we need to immediately think dz dt, the change in distance over time, dz dt. So we have a formula for z. In fact, we could probably calculate what the current distance is at this particular moment. We have x, we have y, we can calculate z. But what we're really after in this problem is the rate at which z is changing, the rate at which that distance is changing with respect to time. That's the unknown. So a moment ago I said I actually like this first formula a little bit better, and the reason for that is because we're going after dz dt. We're trying to find the derivative of z with respect to time. And I don't know about you, but if I had z equals the square root of x squared plus y squared, I would much rather take the derivative with respect to time of a pair of exponential expressions rather than trying to take the derivative of this square root. Certainly we can do that with the chain rule, but in all honesty it's going to be just a little bit easier if we take a derivative of a group of power problems rather than the derivative of a square root problem, which involves the chain rule. Also, it doesn't matter which one we use because these two expressions are functionally equivalent. There are some implications here since we dropped the plus and minus sign after applying the square root. That can be avoided as well, as long as we use our original relationship as z squared equals x squared plus y squared. And to reconnect with our notion of implicit differentiation from last week, remember we said there's a big benefit sometimes in finding derivatives of equations rather than functions, and this guy here represents a nice equation that we can differentiate with respect to time. So we'll do that like we did in the last problem. We'll find the derivative with respect to time of all of these components. So d dt of everything. And again, you'll find that time is pretty common as our differential. Not always, but it is pretty common. So the derivative of z squared would be 2z by itself if our variables matched, but since the variables don't match, we need to offset this derivative by the differential dz dt. That's a good thing because we're looking for dz dt. That's exactly what we would like to solve for in this problem. For the other components, we see much the same, dx dt times 2x and dy dt times 2y. Before I make any substitutions, I'm going to divide both sides by 2z, and I'll have dz dt, what we're after, by itself, and that equals 2x dx dt plus 2y dy dt divided by 2z. And if you recognize the 2 acting at, or the 2 that's a coefficient in the numerator of both of these terms and the 2 in the denominator, those will effectively cancel each other out. Now, just for illustration purposes, I am going to leave those in here for this calculation. I'm going to give myself a little bit of room here, and I'm going to rewrite this fraction taking up 2 lines. I want 2 times our current x value. Now, we did say that x, the horizontal distance, was 180. We're talking about 180 miles. And then our dx dt was negative 120 miles per hour. To that we add 2 times our y distance, which was 225 miles, times our y rate of change, which was negative 150 miles per hour. And in the denominator, let's go ahead and emphasize this. This is a fraction bar that extends the entire way. In our denominator, we need 2 times z. And z, we said, could be the square root of 180 squared plus 225 squared. So now I am using this rule here. I know the distance for z is just the square root of x squared plus y squared. I don't see a great benefit in trying to simplify these piece by piece, so I'm starting up my calculator right now, and I will punch in this expression into the calculator and let it simplify. Now I should be a little bit more careful with my units here. We've got miles and miles as our unit down below. So as I simplify the expression on the top, I'm going to end up with some number, and in the bottom I'll end up with some number, but the unit in the top, well, miles times miles per hour is miles squared per hour, and this one is also a miles squared per hour, and when I add together those two types of unit, I get miles squared per hour in the numerator. In the denominator, I've got miles squared plus miles squared, which is the result, will result in miles squared. But then I'm going to take the square root of that, which will leave me with a unit in terms of miles. And after I have a unit in the numerator that's miles squared per hour and a unit of miles in the denominator, I'll end up with a unit that represents miles per hour. And that's good because that's exactly what we want. The distance, the rate at which the distance between z, or the distance along the z line is changing with respect to time, is going to be measured in miles per hour. All right, so we've got the calculator started up. I'll pull it up now, and we'll try to enter that expression in this calculator. So we've got 2 times 180 times negative 120 plus 2 times 225 times negative 150, and all of this is divided by, let me try this again, 2 times the square root of 180 squared plus 225 squared. And with the exception of the units, I think all of the numbers are in the correct spot. So when I press Control Enter here, we see an end result of negative 192. And from my perspective, I do like 4 decimal points for accuracy. So negative 192.0937. Now here again, considering our units, this does represent miles per hour. And when we're thinking about the problem that we're encountering, what we're seeing is that as these airplanes get closer and closer to the airport, the distance at which they, or the rate at which their distance is changing at this particular moment is 192 miles per hour. So they're getting closer to one another at a rate of 192 miles per hour, even though one is flying at 180 and the other is flying at 225. So I don't know if this has a whole lot of meaning to you or to anyone else in the aviation field, but at least we're learning the process at this point. How can we determine the rate of change based on essentially an unrelated variable relative to 2 known positions in space? Now, the textbook does offer a procedure for related rate problems, and it may be worth your while to write this down and reference it. But personally, I find that just practicing and establishing your own routine often works a little bit better. I'm more than happy to share with you my techniques and to reference these steps in class. But in all honesty, I'm just going to show you my techniques and my procedure, and hopefully that resonates with you. Hopefully you're able to establish your own technique as well. So let's try another example. This time we're not using dt as our differential. Now, one of the first things that I like to do is I like to find the overall formula for the problem that we're facing. And in this particular case, we're being told that sand is falling into a pile, and the pile is in the shape of a cone, this conical pile. And what we would like to know is if the sand is falling at a rate of 120 feet cubed per minute. Now that's interesting. Feet cubed, that's a measurement of volume, but we also have a measurement of time. So we're talking about the change in volume over time. We've got a dV/dt on our hands. This is a dV/dt rate. So I think I was misled when I first read this problem. This will use time as our differential. The question becomes, how fast is the height of the sand pile changing? Well, fast again is a rate, so we're talking about the change in height with respect to time. And we know that this is happening, or we're going to determine when this is happening, when the actual height of the pile, h, is equal to 10. So if I take all of these little context clues into consideration, we're talking about a cone, we're addressing its volume and its height. Let's see if we can write a formula that relates the volume of a cone to its height. And in an ideal world, you'll have these area and volume formulas memorized, such as the distance formula from before and the area formula of a circle. But I don't think it's unreasonable for me to provide you with an area formula reference sheet for our next test. But anyway, the volume of a cone is 1/3 times pi times radius squared times h, where radius is the circular radius of the base and height is the measurement from the base of the cone to its peak. So we've got this cone that's formed. The height is measured from at a 90-degree angle from the bottom of that cone to its peak, and we've got a radius here and a height. Now, you might be a little bit concerned here, as I was initially. This volume formula requires two variables, r and h. And as I read through the problem, I only saw information on h. But as I reread the problem, we were told that the radius is always 3 times that of the height. So this is an additional piece of information that makes our problem a little bit easier. The radius is always equal to 3 times the height. So I'm going to rewrite this formula as volume equals 1/3. In fact, I'll probably combine 1/3 and pi since they're both constants. Pi thirds times 3h quantity squared times h. And I'll condense this even more. Pi thirds times 9h cubed, because 3h squared is 9h squared times another h, which makes 9h cubed. And then finally, just to clean it up one more time, this coefficient of 9 times pi over 3 leaves us with 3 pi times h cubed. Since t is our differential, I'd much rather apply this differential to this formula down below than trying to apply it to any one of these above. So here again, this is an example where algebra is really the important component of our calculus class. This orange ink is representing our calculus work, but everything we've done so far and moving forward after this first step will be algebra based. So here we go. The derivative of v with respect to time, we don't know that, so we'll just call this dv dt. The variables didn't match, so we have to go with the differential here. The derivative of this expression, well, 3 pi is a coefficient. It's a constant coefficient, so I'll push that out to the front. The derivative of h cubed would be 3h squared, but since the h and the t disagree with one another, they're not the same variables, we're going to offset this by our differential dh dt. So if we clean this up with a little bit of algebra, we have 9 pi h squared times dh dt. And we were looking for dv dt. That was we were supplied with dv dt. That was 120 cubic feet per minute. We were supplied with the height, 10 feet per minute. 10 feet squared. What we're looking for is the dh dt. We don't know dh dt. So by establishing our derivative rule, formula for this example, and substituting the known quantities for dv dt and for h, we now have an expression that we can actually solve for dh dt. So I've run out of room, and I'll report this up here. I'll give myself some extra space this time because of the fraction. But we have 120 feet cubed divided by minutes. 120 divided by, now 9 pi times 10, that's easy enough to do. That's 90 pi feet squared. So dh dt, we can probably figure out what that unit ought to be, but we'll come back to that in just a second. dh dt is now isolated because we've divided this to the other side of the equation. And if we have feet cubed per minute divided by feet squared per minute, essentially 2 of these feet units will cancel with 2 of these feet units, and we're going to be left with feet per minute as our unit. And I'm fairly certain that that's desirable here because we're looking for the rate, how fast the height pile is changing. And since this is a rate, it's a measurement of the height in feet relative to time in minutes. So feet per minute is the unit that we want when we're done. Now this is actually okay as an answer, 120 over 90 pi. That's a precise answer. But if decimals are what we're after, something perhaps more meaningful in an engineering sense, it might be nice to have the decimal equivalent or approximate. We've got 120 divided by 90 pi, and that's 0.4244. 0.4244 feet per minute. So we know that this sand pile, when it gets to be 10 feet tall, is increasing in height at almost half of a foot per minute. And it's also worth noting that that rate at which the height is changing is based on how quickly the volume is being added to the height. So evidently this larger collection of sand at the top is flowing at a very precise and constant rate, 120 cubic feet per minute. So as long as that flow, that rate is constant, then the height is changing at this particular speed at that particular moment. Now this video is getting quite lengthy, so I'm going to stop it now and continue on with example 4 and beyond in the next one.